I think we can start the class right now. So meanwhile, if you have any doubts in the previous class or the course content covered in week 1 or week 2, you can ask right now and maybe I can try to address that while others join. So let's start with today's class. So in the earlier lecture, we just looked upon the introduction to the course, that is the chemical process control. And then we studied about Laplace transform. That was a prerequisite to move ahead in the course. So we just covered Laplace transform briefly and then solved few of the numericals related to Laplace transforms. So yes, Laplace transform was defined as an integral, that is integral of the function whose Laplace transform we want to find, then product of e raised to minus st dt, and the integral was bounded from 0 to infinity. Then using this simple formula, we calculated Laplace transforms of basic functions, and using that formula we can generate a table of such kind of Laplace transform that we can use directly. Later we have few of these properties of Laplace transform that can be useful to ease the in order to use the transformation in order to use the Laplace transformation for more complex functions. Then we were looking into a few of the numericals related to Laplace transforms. So today we will be starting with the content of week 1 as well as week 2. So in this lecture I will just briefly cover the contents of week 1, and then I will cover the contents of week 2 and then solve the questions related to week 2 so that it would help you to solve the assignments of week 2. Meanwhile, if you have any doubt related to the assignment of week 0, week 1, you can week 0, week 1, week 2, you can ask me. So in week 1, we will be mainly covering the basics of process control, the motivation behind it, and then different kind of models around this. And then we will also cover the common control strategies. So just to motivate for the course, we are considering an example of this level control in a tank. So we will be discussing about what does process modeling mean. So given any process, we can have a schematic and we can just denote the input and output stream. So if we are having a tank as shown over here, and it is filled with water until height h, and there is an inlet to the tank that we denote it as F in, that is flow in, and then we are having an outlet out from the tank, that is flow out, that is denoted as F out, and then we are having a valve in order to control the flow through the tank. However, in this we aren't able to control F in, we can only control F out with the help of this valve. So if I have to write a simple process model that can mimic this system, I can always use the basic conservation laws, that is conservation of energy or conservation of mass. So from the conservation of mass, we can write that is the flow in minus flow out will be equal to the amount of accumulation within the tank. That is, we can write the flow in, that is the flow rate inside minus flow rate outside, will be equal to area into the rate of change of height, where h is the the level of the water. So such kind of equations are known as process models, because they mimic the performance of the model. And ultimately, for process control, we will be using one or other form of this model to do further studies. So basically, in order to develop so over here we can see that this is a first order derivative, so such a model is known as first order model. And if we take the Laplace transform of this equation, then we can get the same process model in terms of S domain. So over here all the parameters will be a function of time, and in the S domain all the parameters will be a function of S. So using the Laplace transform of this equation, we can get the transfer function model that can be further used for further studies. So now in terms of control philosophy, since we are not able to control the flow inlet, that is not up to our hand, so we call this term as disturbance. So whatever parameters or variables that we can't directly control, we treat them as disturbance. So then there is this another variable, that is manipulated variable. So we can control the level of this tank using this outlet valve. So since by using this outlet valve, we can manipulate the flow output through which we can control the level of the tank. So that is why this F out, we call it as manipulated variable, and this valve we call it as controller. Then similarly, since we are controlling, our main objective is to control the level in this tank, that is H, we call this variable as control variable H. And then to monitor the level in the tank, we can have this level indicator, that is an LI. LI is basically level indicator. So in order to control the level in the tank, we will basically measure there are different kind of strategies to control the level in the tank. So the one thing we can measure the level of the tank H, and if it is beyond our expectation, then we can simply open the outlet valve and let the water flow outside the tank. That is, we can manipulate the level, that is, we can control the level of the tank by changing this manipulated variable. Then the other thing is, there is only one source of disturbance which can affect the controlled variable. Over here it is disturbance. So alternate ways we can monitor the disturbance, and once the disturbance changes, accordingly we can control the outlet valve without measuring this controlled variable. So based on this disturbance, we can just change the outlet valve and let the water flow and ultimately control the level of the tank. So that is another control strategy. So both of these control strategies that I discussed right now are termed as feedback control and feed forward control. So we will discuss this feedback control and feed forward control in a bit more depth. So a schematic representation in terms of block diagram for both of the system is shown in the figure, that is feed forward control and feedback control. So to again reiterate, if this is the tank, this is the flow rate, this is our F output, flow inlet, and this is my height that we want to control. So for the first approach that we discussed was, in order to control the height of the tank, what we can do is we can directly measure the level of the tank, and on the basis of this we can control the outlet valve that's basically, if the level increases, then we can open this valve and let the water flow it, so the level in the tank will be controlled. So over here, since we are measuring the controlled variable, so basically we are taking the feedback from the system. So let's say whenever any disturbance occurs, that is, if the flow in is increased, the level of this tank will start on increasing. So there will be a deviation seen in this steady state. There will be deviation seen between the steady state level of the tank as well as the current level of the tank due to this disturbance. So that deviation will be captured in the controller, and on the basis of that deviation we can try the opening percentage of the valve. So since we are taking the feedback from the system after the disturbance has occurred, we call this type of control strategy as feedback control. Then in another control strategy, we are having this disturbance. So over here we will keep on monitoring the disturbance. So once the disturbance changes, that means we already know if the disturbance changes, the level in the tank would change. Then on the basis of this disturbance, we will change the opening of the valve and let the water flow through. But in order to know the effect of the disturbance on the height and ultimately the valve opening, we need to have a process, we need to have a model. So basically we will be feeding the disturbance to an alternate model that will show us how much the level will change in this system, and based on that level change we can find the opening of the valve and basically ultimately control the system. And such a kind of process model is known as such a kind of control strategy is known as feed forward control. So yes, over here we are having the schematic. So in the feed forward control, we can see that if this is the disturbance, so the disturbance will affect the process, and this disturbance is then fed to controller, and on this controller action will take the control action on the basis of this disturbance, and then that control action will be fed to process in order to control the output Y. Similarly, in case of feedback control, we have a set, we give in any controller we give the set point to the system, and then there is this manipulated variable, and this disturbance variable will directly affect the process. And once the disturbance has occurred, we will be measuring the over here we will be measuring the output level under the effect of this disturbance, and then again feed it back to the controller. So the controller will measure the deviation of the set point as well as this feedback variable, and then on the basis of that it will take the control action U. Whereas in case of this feed forward controller, there is this only input, that is disturbance. So it will measure the disturbance, and then on the basis of set point it will take the control action. Whereas in case of feedback controller, it will measure the output variable, that is the height of the tank in this case. So this is the major difference between feed forward as well as the feedback control system. If you have any doubts, you can just write it in the chat box. I'm monitoring that. So if we take a look on the advantages and disadvantages of both the strategies. So here I'm having notes from the lecture. So in the feedback control, we can directly monitor the effect of the disturbance. So since we are measuring the changes in height by using any instrument, that kind of system we call this direct monitoring. So moreover, this system is robust since we can measure the effect, and since we can measure the effect of the disturbance on the level and then use that deviation in the level to control this valve. Similarly, in case of this feed forward control, this is a proactive strategy, means as soon as disturbance occur, we are taking the control action. Whereas in case of this feedback control, once the disturbance has occurred, it will go through the process, and then we are measuring the deviation in the process output. That is basically we are reacting to the changes in the process output, not the input. That is why we call this as reactive strategy, and that is one of the limitations of this feedback control. So the control action will only be taken after the effect has been felt on the output variable. And in many cases, such kind of disturbances such kind of control action can destabilize the system. So basically, if the deviation variable is very high, then in order to account for this deviation variable, the control valve opening can destabilize the system. Then if we take a look on the limitations of the feed forward control, then the feed forward control lacks direct monitoring, since we are not measuring the output variable, then this is sensitive to prediction model. So for feed forward control, we need a prediction model that can quantify the effects of the disturbance on the output variable. That is why we need a prediction model, and in many cases an accurate prediction model won't be available. So that there can be error due to these prediction models. Then again, there can be unaccounted disturbances can destabilize the system. So in the case of this level control, we are sure that there can only be a single F input that can be a disturbance. There can be, but in other systems, there can be multiple disturbances that can be difficult to measure or that are not known to us. So such disturbances need to be accounted for in order for a perfect control strategy. But since we can't account them, they can destabilize the system. So that is one of the limitation of the feed forward control. So in order to overcome the drawbacks of both the strategy, we can also use a common strategy that uses both of this. That is basically feedback control as well as the feed forward control. So what basically we do it, that is, in that strategy we measure the output, that is basically the height of the tank as well as the disturbance, and then on the basis of both the flow, both the disturbance as well as height, we take the control action. So that is the main advantage of this combined strategy of feedback and feed forward control will be that it is a direct monitoring, it is a proactive approach, it is robust, and it is unaccounted disturbances can be handled. So basically the limitations of all the both this previous strategy can be tackled by using this feedback plus feed forward control strategies. But again, for this feedback and feed forward control strategy, we need a additional hardware, and also it is difficult to coordinate this feedback and feed forward control system. That is basically how should we emphasize more on which of, whether we should give more importance to this feed forward control action or the feedback control action. So we need to basically coordinate both of these things, and getting a optimized control strategy for that uses both this feedback and feed forward control strategy can be a difficult task. So basically we need to coordinate the feed forward and feedback control action, and that can be more difficult. Now earlier we were discussing the case of this surge tank or level control unit tank. Now we will take a look on another simple example of this distillation column. So just to define both of these things again, so feed forward control will respond only after it detects a deviation in the value of controlled output from its desired set point, whereas in case of feed forward controller, it detects the disturbance directly and then takes an appropriate control action in order to eliminate its effect on the process output. So there is a question that what is a prediction model? So we will take a look on the prediction model. So prediction model can be a model. So over here we are having this process model. So if we take a look into this process model, over here H is the output of the system, then we can say that time as well as this F input are the inputs of the system. There can be additional inputs, let's call it as H. So we can develop a model such that given this input we can generate this output. So such a model is known as prediction model. That is basically we need to find a model such that output is a function of input. So whenever we have a new input, we can just feed this input into this model, and corresponding to that we can get the output. So such a kind of model we call it as prediction model. Now in case of any of this strategy, let's say the level control example, in order for this feed forward control action, we can have the model that is the height of the tank, then there is this model F which can have this prediction model F input. So once a disturbance is detected, we can find the corresponding height we can find the height corresponding to this disturbance. So that is why we need a prediction model in case of this feed forward model, in the case of this feed forward control. So this this prediction model we will study in the later classes, that are the first order model, second order model, and the higher order models. So these models are basically called as the prediction models. So yes, now let's take a look on this distillation example. So over here we are having this feed flow rate, then the output is the distillate, and as well as the bottom. And in this case our main objective is to control the outlet of the distillate. Basically, let's say we want to control the flow rate of the distillate, and in this case the feed flow rate is the disturbance to the system. So one way to control the outlet through the distillation column of the distillate, that is D, is through the feedback controller, and then the other way is the feed forward controller. So since in this case our controlled variables are distillate flow rate D, we need to monitor it. So we will measure this distillate flow rate by using a flow meter or flow indicator, and then feed it back to the feedback controller. And on the basis of this distillate flow rate, we can use a controller over here, basically a control valve on the outlet that can basically control the reflux through this reflux into the distillation column, via which we can control the outlet flow rate. So such a kind of system we can call it as feedback controller. The other approach is to control the outlet of the distillate by directly measuring the disturbance. So this feed flow rate is the disturbance. So we are monitoring the disturbance. Then on the basis of the prediction model or any simple model, we can know its effect on the outlet flow rate, and then correspondingly we can change the control valve opening in order to control the flow rate of the distillate. So this is known as feed forward controller. So just a comparison of both of these controllers. So the feed forward controller, we will be feeding the disturbance to the controller, whereas in case of this feedback controller, we will be feeding the controlled output to the controller. And on the basis of both of this action, we will be getting the manipulated input that will be ultimately fed to the process model in order to maintain the set point of the system. So on the basis of the earlier defined control strategy, we can define this feedback control law. So basically this control law states that given any disturbance or changes in input, how will the control action or how will the system stabilize. So basically the first step will always be the measurement of process output, that is pressure, temperature, flow, level, composition using a suitable measuring device. So let's say if we are controlling the level in the tank, then we need a level indicator or the level controller. If we are measuring the flow rate outside the distillate of the distillation column, then we need a flow indicator. So basically these are the measurement devices. Then we need to compare the process output and the desired set point. That is, we need to measure the height of the tank with our expected height, that is our set point. And then basically we need to calculate the deviation error. So from the flow indicator, we will be getting the flow measurement, and then we will be calculating the deviation between the flow measurement as well as the flow set point, that is desired set point. And then on the basis of this deviation error, we will be feeding it to the controller, which calculates the appropriate control action that needs to be taken. So the controller will take the control action, and then this control action will feed the value to the final control element. So the control element in this case will be the controller. So basically a controller translates the control action into manipulated form of process input. So yes, this is the basic schematic of a closed loop feedback control. So we provide the set point of the system, then there is a controller, then there is this final control element that basically controls the measured quantity, and then we will be feeding the input to the system and we can get the corresponding output. There also is disturbance to the system, and for feedback controller we need to have this measuring device that will measure the output of the system. So this was the feedback control in brief. So yes, you can take a look on the major advantages and disadvantages of both the feed forward as well as the feedback controllers. So yes, feedback controller takes the corrective action before the process feels the disturbance. So such a kind of system is good for sluggish systems or the system with large dead time. Then feed forward controller does not affect the stability of the process. However, there are demerits to this feed forward controller. That is basically we need to account for all the disturbance of the system. Then it is sensitive to variation in process parameters. So if any of the process parameters changes, then the prediction model or the model of the process will change. So that also needs to be accounted for. That is why we say that it is sensitive to variation in process parameters. Then again, it requires a near perfect model of the process. Now in case of feedback controller, we don't need to measure the disturbance, and it is insensitive to mild errors in modeling, then insensitive to mild changes in process parameters. But this feedback controller will only act after the process feels the disturbance. That is, corrective action will be taken only after the disturbance is felt by the system. Then again, this is bad for sluggish system or system with large dead time, and it may affect the stability of the system. So this stability part we will discuss later in the, I think, after 3 to 4 lectures. So how this feedback controller affects the stability of the process. Now there can be two kind of control objectives. So right now we studied two different kind of control strategies, that is feedback control and feed forward control. Now there can be two kind of control objectives. There can be two type of goals or targets that we want to achieve by using those control strategy. So the first one is regulatory problem and the second one is server problem. So regulatory problem, we also call it as disturbance rejection. And server problem, we can also call it as set point tracking. So let's say if we are having a reactor, and our main aim is to control the temperature of the reactor, that is temperature of the reactor. So our aim is to maintain the temperature of the reactor to, let's say, 100 degrees Celsius. And then there can be additional disturbances in terms of flow input to the reactor, then the cooling water flow rate, that is, let's say, call it as C in. So we can call this the flow rate of the cooling water, temperature of the cooling water, as well as the flow input to the reactor as the disturbance variable. So no matter what disturbances I provide to the system should always maintain the temperature of the reactor to 100 degrees Celsius. So over here we can call this 100 degrees Celsius as the set point of the system, this as the disturbance. So our controller should act in such a manner such that no matter whatever the disturbances are there, the temperature of the reactor should always be maintained to 100 degrees Celsius. So basically we want to regulate the temperature of the reactor to 100 degrees Celsius by rejecting whatever disturbance I am providing to the system. So when we want to reject this disturbance, such kind of control objectives, we call it as regulatory problem. That is basically when the set point remains constant, that is in this case the set point is constantly maintained at 100 degrees Celsius, while the disturbance forces the process to move out of the track of the set point. The objective of the control system will be to reject the effect of disturbance as soon as possible and steer the output back to set point trajectory. And such a kind of control objective we call this regulatory problem. That is basically we want to reject whatever disturbance is occurring. Then another kind of control objective is known as servo problem. Over here, while the set point of the process undergoes a change, while the disturbance affecting the process remains the constant. So if the flow input of the system and the cooling water temperature flow rate, that is basically disturbance to the systems, are kept as constant, and we want to change the temperature of the reactor. Let's say if I'm taking let's consider a case of polymerization reaction. So in order to start the polymerization reaction, the initial temperature should be high so that the reaction initiation could occur. So initially I will just increase my temperature to, let's say, 100 degrees Celsius. But after the reaction has started, basically the reaction has initiated, I would like to lower the reaction temperature, that is from 100 degrees Celsius. Let's see if I want to bring down the temperature to 80 degrees Celsius. Then earlier my set point was 100 degrees Celsius. Now we are changing it to 80 degrees Celsius. That is, my new set point will be 80 degrees Celsius. So the control action of the system should be such that it should bring the set point of the system, it should bring the temperature of the reactor to this new set point, that is 80 degrees Celsius. That is, we are basically tracking the set point of the system. So such kind of system we call the set point tracking or servo problem. So yes, there are basically two main kind of control objective, that is regulatory problem as well as servo problem. Now we discuss this prediction model in brief. So there can be different kind of prediction model. So in earlier case of this level control example, we wrote the prediction model as flow input minus flow output is equal to accumulation term, that is AdH by dt. So this was obtained by mass conservation. So basically we know the physics of the system and we are developing a model using this physics of the system or the first principle based modeling. So such kind of modeling we call it as white box model. Now let's say if I don't have these equations, okay, I don't have this mass conservation equation now, then how can we model this system? Then let's say I can just perform few of this experiment and I can get an empirical model, that is y is some function of, let's say, kp 1 minus e raised to minus 1 upon tau. Now this is an empirical model and here are these parameters, this kp and tau. That is, basically we can write the empirical model as a function of kp and tau, and I don't have the values of this kp and tau. So what I can do is I can just perform few of these experiments manually and then try to fit the data, and on the basis of that data I can try to estimate these parameters kp and tau, and then fit it and then put these parameters into this empirical model and then get the estimate of the output. So yes, so such kind of models are known as empirical model, in which we are having a rough estimate of the model, but we get the model parameters from an experimental model. Now the third kind of models will be the black box model, in which we don't have this empirical model or this first principle based model. So so over here we can only generate, we can perform different kind of experiments on the system, then get an input. We can get an input as well as output data, and then we can use such black box models in order to estimate the output of the system. So this black box model take any form. So we can also use this linear regression, that is y is equal to, let's say, mx plus c. So this is a linear regression model. So this model can be called as a black box model. Now let's say if we know that this is not a linear correlation, we are having a polynomial correlation, so we can also write it as a1x1 square plus a2x2 plus c. So this is a polynomial model. Again, this we can call it as a black box model. So we can define n number of black box model in order to mimic this system. So yes, there are basically three kind of process models or prediction model. That's basically white box model, gray box model, black box models, that we use to ultimately control the system, to mimic the performance of the actual system. I hope this much is clear. So this was all the content from week 1. Then there is this special note that based on the experience, it turns out that the feedback control strategy is very robust and requires less or minimum instrumentation typically preferred and is a typically preferred choice for control strategy. So in most of the systems, we use this feedback control strategy. However, only for the extreme cases where the operating point is very close to stability limit or the safety limit, where we cannot allow any reactive action to be taken. So for those cases, we need to have this feedback control strategy, and we can also use then feedback plus feed forward control strategy. So most commonly in chemical control system, we use this feedback control strategy. So in today's lecture, until now, we covered this content of this week 1. So now we will just quickly cover the content of the week 2 and then solve the numericals related to week 2. So if you have any doubt related to the content of week 1, you can ask. Then we can start on the basics of this week 2. So let's start with the contents of week 2. So first we'll be covering this first order dynamical system. So first order system is a dynamical system whose dynamics are given by the first order differential equation. So in the earlier case of level control, we saw that the differential equation could be written as F in minus of F out is equal to A dH upon dt. So this is a first order differential equation. So such a kind of system is known as first order system. So couple of examples, we can call it as level control can be called as a what first order system. Then if we are having a heated tank, that is basically we are having a tank and we are controlling the temperature of the tank. So such a kind of system, heated tank, also we can call it as first order system. So in general, all the first order system can be represented using this first order differential equation, that is a1 dy by dt plus a0 y b f of t, where f of t can be any forcing function. So it can be 1, it can be any function of time, it can be any nonlinear function of time also. Now if we want to find the response of this system, we need to have a model that correlates y as the function of input. So over here we can call this as the input of the system, that is f of t. Let's call this function as g of t. Now in order to find such kind of solution, we had studied about the Laplace transform. So we can take the Laplace of this equation, and basis of that we can get the transfer function model that can help us correlate the inputs to the output. Now on the basis of the values of a1 and a0, we will study different cases on how to do that. So over here, if a0 in the earlier term was not equal to 0, we can just bring it into the denominator and we can write the general form of first order system by this equation. And if a0 equal to 0, then we can write the earlier first order differential equation as this equation. So in both the equation, you can see that the time is the independent parameter, y is the dependent parameter, we can call it as output of the system. Then there are these parameters of the system that we are defined, that is tau and kp. So this kp and tau are the parameters of the system if a0 equal to 0. If a0 is not equal to 0, and if a0 equal to 0, then we are only having a single parameter, that is kp. So such a kind of system in which a0 is equal to 0, we call it as a capacitive process, or we can also call it as an integrating process. because if we take the Laplace transform of this equation, we can see that the response will be having what the transfer function will be having a term of Kp by S. So since there is the presence of this 1 upon S, we call it as an integrating action. Now we will see the transfer function representation of this system. So let's say if I'm representing my first order system as tau dy by dt plus y is equal to Kp. This is my first order system, tau dy by dt plus Kp. Kp into, we are having an input, let's just call it as x of t. So here x of t is my input to the system, y of t is the output to the system. Now if I want to convert this into S domain, that is basically find the transfer function. We need to take the Laplace of this equation, that is Laplace of tau dy by dt plus Laplace of y is equal to Laplace of Kp into x of t. So we studied in the previous class that Laplace transform of the derivative will be, for this derivative it will be s y of s minus y of 0 plus this will become y of s is equal to Kp into x of s. Now if we call this y as the deviation variable, that is, we can treat this initial term as simply 0. Then we can again rewrite this equation as tau s ys plus ys is equal to Kp into xs. So we can rewrite this as, these are all capital y of s into tau s plus 1 is equal to Kp into xs. So using this, we can have this form, this kind of form, x ys upon xs is equal to Kp upon tau s plus 1. So this is the transfer function model for the first order system, where ys is the output of the system, xs is the input of the system, Kp and tau are the parameters of the system. So in general, Kp we call it as process gain, and tau as the time constant. So we are naming these parameters, and such kind of representation we call it as transfer function representation. So now, and we denote this as g of s. So transfer function we denote it as g of s. That is basically we are having g of s is equal to y of s upon x of s. Now whenever we want to find any output y of s, we can just simply use this correlation, y of s is equal to g of s into x of s. We will be having the transfer function model or the prediction model of the system, that is g of x, and on the basis of whatever input that we are providing, we can find the corresponding output. So this was the case when a0 was not equal to 0. Similarly, we can find this similar transfer function for this first order system where a0 is equal to 0. And over here we can see that the transfer function will become Kp by s for this system. So if a0 equal to 0, we are having this Kp by s term, and if a0 equal to 0, then we are having Kp by s. If a0 is not equal to 0, then the transfer function will be Kp upon tau s plus 1. So ultimately this transfer functions gives the relationship between the input and the output. So the output is always denoted by y and the input is always denoted by x. So again, one thing to keep in mind is that if A not equal to 0, then such kind of processes are known as capacitive. Or integrating processes. We call it as integrating because of the presence of this term 1 upon S. So wherever there is 1 upon S, there will be an integrating action of this transfer function model. So now we can take a look on this liquid storage tank example. Consider this liquid storage tank. Over here we are having an output, and then we are having an input. So the process model, we wrote it as F input minus F output is equal to A dH upon dt. Now in this case, over here we are not having a valve. So what will happen is this flow output is constant. So basically it will keep on the water will keep on flowing out. So basically so this flow output, we call it as, right now it is constant. So this flow output flow rate will always be constant through this tank. And once we are facing a disturbance in the input, so let's say if there is this flow input, if the flow rate increases, then the level of the tank will increase. That is basically the capacity of the storage of this tank. Basically the level of the tank will increase. So such kind of system, we can call it as capacitive process. So basically the flow rate was constant, that is F output, let's just call it as K. If you just put this constant K or any constant in this equation and then find the Laplace transform of this equation, you will get the form where the transfer function model will be of the form of this equation, that is Kp upon S. So transfer function model for this system will become Gs is equal to Kp upon S. So such a kind of system we call it as capacitive process. Now let's say if we are having a valve at the outlet. So basically we can control, we are having a valve at the outlet. So this valve will have some resistance R, then we are having the flow inlet, then we are having the height of the tank. So now the flow output, we can call that it is proportional to the height of the tank and inversely proportional to the resistance that can be provided by any system. In this case, we are calling it as valve. So now if we replace this F output into this equation, F in minus F output is equal to A dH by dt, and then find the Laplace transform of this system, then the transfer function model will be of the form of Kp upon tau S plus 1. Now in this case, you can see that if the disturbance increases, that is the flow input increases, then the height of the tank will increase. So since the height of the tank will increase, we are having this flow output correlation, that is F output is equal to H upon R. That is, since F inlet is increasing, this height will increase, that is basically this height will increase. So basically the flow output will increase. That is, if the flow output increases, then on the basis of this action, the height of the tank will start decreasing. That is, over here we can see that we are having a resistive action. So the resistance is basically, so the resistive, when I say resistive actions, so basically the disturbance or the input tries to increase the level of the tank. Basically it tries to increase the controlled variable, but the outlet flow rate in this case is such that the moment the flow output will increase, the level of the tank will decrease. That is, whatever the effect of this disturbance we are feeling will be negated or will be decreased by the presence of this wall. So basically we are resisting the capacity of the tank to hold the water by using this kind of correlation. So such kind of system is known as resistive systems. So over here, this is the resistive action. Now over here, we had considered this linear correlation, that is, flow output is linearly correlated or linearly dependent on the height of the tank. Similarly, we can consider any kind of non-linear correlation also. That is, let's say the flow output is proportional to square root of height. That is, it will be alpha times of under root of h. So in such a case, our process model will become f input minus alpha root h upon area times dh upon dt. So over here, now we are having a non-linear term, that is h raised to 1 by 2. So finding the Laplace transform of this equation and ultimately the transfer function of this model will become difficult. So whenever we face any non-linear term in the system, we need to linearize the system, basically convert this non-linear term into the linear form. So one way to do this is using the Taylor series approximation. So we can find the Taylor series approximation, that is f of x plus h is equal to f of x plus h of f dots of x. Similarly, we are having this. So we can use such kind of Taylor series expansion or other expansion in order to find the approximation of this term, so that we can convert this non-linear system into linear system, and once we have this linear system, we can find the Laplace transforms. So we can consider all of these three cases where, so the first case was where the flow output was constant, where the flow output was proportional to the height, that is linearly correlated with the height. The third case was where the flow output was non-linearly correlated with the height, that is under root of h. So you would have discussed all these three cases in depth in the lecture. Now there are these two main points that I wanted to emphasize on. So very defining characteristics of the first order system that we studied earlier, the level control tank or any stirred heater tank as discussed in the class, is that they have the capacity to store material and energy. That is, basically they are the capacitive system, as well as they have the resistance to capacity building. So in case of this valve where the flow rate was proportional to height, we studied this resistive action, that is they have the resistance to capacitive building. So this will allow the system to do what is known as self-regulation. So mostly in most of the chemical engineering systems, there will be these two types of storage, that is material and energy storage, and often they will be having also this resistance to capacity building, that is they can be resistive also. So these are two most important features of these first order systems, that is they can store material and energy and they have this resistance to capacity building. Now we will just study different kind of inputs to the system and then move on to the numericals. So we studied that the transfer function of the system can be written as g of s is equal to y of s upon x of s. So this x of s, we call it as input to the system. So now we will be studying what all different kind of inputs are possible in the system. So in this, the first one that we are studying is the step input. So when I say step input, let's say in case of this level control tank, this flow input. So if this is the input to the system, that is, now we are considering this as manipulated variable, that is mv, and let's say for a certain amount of time this flow input was kept constant at 2 meter cube per second. Now at time instant, let's say t is equal to k, I change the flow rate from 2 to 4, and then keep that as constant. That is, at time t equal to k, I'm increasing the flow rate to 4 meter cube per second. So after this, the flow rate will remain at 4 meter cube per second. So at this time instant k, we are introducing a step change of magnitude 2 from 4 minus 2. That is, we are providing a step change of magnitude 2. So such kind of input is known as step input. That is, so if we just shift this point k to 0, that is basically if we write this as t minus k is equal to 0 and this as t bar is equal to 0, then we can denote this step input in generalized form as u of t. So we represent this input by u. That is, at time t less than 0, it will be 0. That is, it is not changing. If we now take a look onto this example, so at time t less than 0, it will be constant at 0, but at time t greater than 0, it will be a constant value of m. So this is my step input. So this is in time domain. Now if we want to convert it into s domain, we can take the Laplace transform of this constant m, and it will be m by s. Now we can straight away use this input into this equation and find the corresponding output. So just to again reiterate, step input is given by this transfer given by this function m by s. Now there is another input, ramp input, in which what we do is after a few times we keep on increasing the manipulator input. So in case of level control example, if the earlier flow rate was 2 meter cube per second, now after some time I keep on constantly increasing the flow rate. That is, earlier it was 3, now I will at time t, at 1 second I keep it as 3, at 2 seconds I keep it as 4, at 5 seconds I keep it as 5. So I'm continuously increasing the flow rate of the input. That is, we can denote it by a constant slope. So such kind of input we call it as ramp input. That is, for t less than 0 it is 0, or else it is at. And the transfer function of this input will become a by s square. Now another kind of input is pulse input, where what we will do is, let's say we were having the flow rate of 2 meter cube per second, but just for a very brief period we increase the flow rate to 4 meter cube per second and then quickly bring it back down to the original value, that is 2 meter cube per second. So over here we observe a pulse in the input of the system, so we call this as pulse input. And in time domain we can represent it as delta t, that is Dirac delta function. And if we take the Laplace transform of this Dirac delta function of magnitude 1, so over here the magnitude is 2, but if the magnitude is 1, then we can find the transfer function as u of s is equal to 1. Similarly, we can have this sinusoid input also, where the input changes by this function a sin omega t, where a is the amplitude and omega is the frequency. And then corresponding to that sinusoid input, we will be having this input in s domain, that is a omega upon s square plus omega square, that is obtained by taking the Laplace transform. Now we will cover this response to the step input for a first order system. So we know that the transfer function model of a first order system is Kp upon tau s plus 1. That is basically transfer function model. We can also write it as ys upon x of s. So this is my output equation for any given input. Now let's say if we are introducing a step change in this first order system. That is, let's just call this u. So earlier my manipulated input was constant. Now at time t equal to 0, I increase the manipulated input to some value and then keep it as constant. Okay, now we want to find the effect of this step change on the output of the system. So let's say earlier my output, if the input was 0, I'm calling it output also as 0. Now the moment I introduce the step change, I want to find the output of the system. So we studied that the formula of this input for this step change is, you can call it as x of s, that is input of the system, will become a by s. Let's just call this magnitude of step change as a. So corresponding to this step change, we can write the input as xs is equal to a by s. Now we can replace this xs into our earlier this equation. We can replace this over here. So we can get the output as y of s is equal to a times kp upon s into tau s plus 1. Now we can write this in terms of partial fraction a by s plus b upon, let's say, tau s plus 1, and then take the inverse Laplace transform of this function, and then you will be getting the solution in terms of time domain. That is, the solution that we will be getting will be yt is equal to a kp upon 1 minus e raised to minus of t by tau. So corresponding to this step change of magnitude a, we can get this response of the system by this equation. So this kind of response, we call it as a first order response. So you can remember this equation. So if we plot this function, so just if you plot this in this function, so it will be an exponential curve. So it will vary in such a manner. Ultimately, after a few time, it will be constant. That is, it will reach a new steady state over here. So now we can study the characteristics of this first order response. That is, at t equal to 0, we had introduced the change in input, and correspondingly we are plotting the output of the system. So after few time, this thing will become constant. That is, we can say that at t tends to infinity, this change, the response will become constant. So if you just put t equal to infinity in this equation, so it will become 1 upon infinity. So basically that will become 1 upon e raised to infinity. So this term will become 0. So t equal to infinity, y of t, we can find it as 8 times kp. So basically this difference is a kp. So this height we can call it as a kp. So basically for any step change, if we want to find the deviation from the steady state value, we can simply write it as kp into a into kp. This is nothing but y of infinity minus y at time t equal to 0. So on the basis of this, we can find the process parameter, that is kp, that we are calling it as process gain. So when we say process gain, that means if my output was at 0 and I introduce a step change of any magnitude, then the gain in the output will be of the magnitude of kp. If the magnitude of the step change is a, then the magnitude of the gain will be a times of kp. So that is why we call this as process gain. Now using this, if we want to find the value of time constant, so that we can put the value of akp over here, and then we can come to a correlation that the time constant is defined as the time at which the response of the system is 63.2% of the steady state value. So if this thing is 0.632 times of AKP, so the time corresponding to this response, we call it as tau. So if the steady state value is by infinity, then the time taken by the system to reach the 63.2% of this value is known as time constant tau. So if we again find the response at time t equal to 2 tau, we can, over here we are having y is equal to 0.632 of ys. Similarly, we can find at 2t tau, 3 tau, 4 tau, and if we keep on doing this at 5 tau, we can see that the response will become 0.99 times of steady state. That is, at 5 times of time constant, we can approximate that the system has reached the steady state. So these two correlation we need to remember. The first one is a time constant at time is equal to time constant tau. The response will be 63.2% of the steady state value. And at time of 5 tau, the response will be 0.99 of the steady state value or the ultimate value. These two correlation we need to remember. So this was the response of the first order system when the input was the step input. Similarly, we can find the response corresponding to different kind of inputs. So if we are given a first order system and we are providing a first sinusoidal input to the system, then we can find the response by using again this equation, using the transfer function and then taking the inverse of this equation. That is basically we need to take the inverse of this equation by using the partial fraction, and corresponding to that we will be getting this function in time domain. So that is the sinusoidal response of the first order system. Now in this equation, if we want to find the process gain or the amplitude ratio, we can see that as time tends to infinity, this entire term will become 0. That is, the steady state value of the system will now become AKP upon 1. So the steady state value of the system will become AKP upon under root of 1 plus omega square tau square sine omega t minus of 5. That is, if earlier my amplitude of the sinusoid was A, that is the amplitude of the input is A, the amplitude of the sinusoid will either decrease or increase based on this parameters omega and 5. So either it can increase or it can also continuously keep on decreasing. That is, the ultimate steady state of the sinusoid response can be obtained by this equation, and the amplitude ratio, we can find the ratio of the amplitude of the input. That is, this is the amplitude ratio of the input and this is the amplitude of output. So the ratio of output upon input, we call it as amplitude ratio. And for sinusoid input, the amplitude ratio will be this term Kp upon under root of omega square tau square plus 1. So this is another equation that you need to remember. You can easily derive this also. So now we looked on to the theory of week 1 and week 2. Now we will solve the numericals related to those. So if you have any doubt related to the theory of the previous 2 weeks, you can ask later, and then we can start solving few of the numericals. So do you have any doubt? You can write it in chat box. Or else we can just start with the question solving straight away. So this is the first question that we are dealing with. So the question is, a unit impulse response of a first order system with time constant tau and steady state gain is given by dash. So this is a simple derivation that we will again derive. So we had looked onto the response of step input as well as sinusoid input, but in this question we are asked to find the response corresponding to the impulse response. So for impulse response we can write this as u of t is equal to delta t. Corresponding to that, u of s will be 1. And for the first order system, the transfer function, that is g of s is equal to y of s upon x of s is equal to, we write it as kp upon tau s plus 1. Now in this question, we have been asked to find the response of a first order system corresponding to this impulse input. That is, we can replace this x of s by this input, that is 1. Corresponding to that, we can write the output as kp upon tau s plus 1 into 1. Now to find the response in time domain, we need to take the inverse Laplace of this. That is, y of t is equal to Laplace inverse of y of s will be Laplace inverse of kp upon tau s plus 1. So this thing we can also write it as kp upon tau, we take it as common s upon 1 plus tau. And we know that the Laplace inverse of 1 upon s plus a is e raised to minus at. So using this inverse Laplace formula, we can find the response of this first order system for this impulse input as, it will become kp and tau are constant, and corresponding this 1 upon s plus tau, it will be e raised to minus of at, and in our case a is 1 upon tau, that is 1 upon tau. So this is the impulse response, that is kp by tau e raised to minus t by tau. So we can see that option D is the correct option in this case. It's kp upon tau e raised to minus t by tau. Now we will take a look on to the second example. So this is a fairly simple example. So I will just solve this online, and and for other advanced examples I will just give you time to solve. So over here the question is, a system has a transfer function given by this equation. When a step change of magnitude m is given to the system input, the final value of the system output is measured to be 120. The value of m is dash. So again in this equation we are providing the step change of magnitude m, that is the input u of s. We can write it as m upon s. So this we already covered, that for the step change the input will become a by s or m by s, whatever the magnitude of the change that we are providing. Then y of s is equal to g of s into x of s, and in this question we have been asked to find the final value of the system. So we'll just replace this transfer function over here. So this transfer function, you can see that on the denominator we are having this 12s plus 1 term, that is similar to the first order transfer function 1 upon tau s plus 1 term. Additionally we are having this e raised to minus 4s term, that is basically we are having a delay in the system, that is this term corresponds to the delay in the system. So basically we can call this system as first order system plus time delay, that is FOPTD, first order plus time delay kind of a system. So again we can just replace this over here, e raised to minus 4s upon 12s plus 1, and xs was m by s. Now in the earlier class we studied that the final value of the system can be found out by this final value theorem, that states that y of infinity will be limit s tends to 0 as ys. So in order to find the final value, that is y infinity, we can just multiply it by s, that is s into 3 into minus of 4s upon 12s plus 1 into m by s. And in this case, we have been given the final value of the system as 120 and have been asked to find the magnitude m. So this we can put it as 120 and just cancel out s, and we have to put the value of s as 0. So over here we can put s as 0, and over here also we can put s as 0. So basically we will be having 3 into 1 upon 12 into 0 plus 1 is equal to 1. Over here we are having m is equal to 120. So basically this term will be 1. So we are having 3m is equal to 120. That is basically m is equal to 120 by 3, that is 40. So the value of m we found out as 40. So this question discussed about the final value of the system, and also we covered the step change. So step change is represented by m by s. Now this is a very similar question to the previous one, in which we are given this transfer function. Then we are having a unit step input, that is the input in this case will be 1 by s, and then the output value immediately after the step input. So over here we have been asked to find the value at time t equal to 0, that is u of 0. So we can simply find it by using the initial value theorem, that is by putting s tends to infinity s ys, that is limit s tends to infinity s g of s is 10s plus 1 upon phi s plus 1 into xs was 1 upon s. So you can cancel this, and then from both of these terms you can take ss common and write it as 1 by s. Similarly over here it will be s into 5 plus 1 by s. So this s will get cancelled out. We will put the value of s as infinity over here. So this term will become 0, and the initial value of the system will be 10 by 5, that is 2. This question 4 and question 5 are very similar. So let's just discuss either of the question. So let's just discuss question number 5, and then we will solve a couple of more questions. So I will just take a break of 5 minutes. Meanwhile, you can solve this question number 5. So this is a fairly simple question, and you will encounter more of this question in this first order system. So let's solve this question number 5. So over here we are given a thermometer initially at 100 degrees Celsius is dipped at time t equal to 0 into an oil bath maintained at 150 degrees Celsius. If the recorded temperature is 130 degrees Celsius after 1 minute, then the time constant of the thermometer is dash. So let's just make a plot of this system. So over here we are having t equal to 0. Then over here we are measuring the temperature. So we have been given that a thermometer is initially at 100 degrees Celsius. So let's just call this as 100 degrees Celsius. Then at time t equal to 0, it is dipped into an oil bath maintained at 150 degrees Celsius. So over here, the thermometer is dipped into an oil bath of 150 degrees Celsius. So this is 150 degrees Celsius. So corresponding to this temperature change, solely it was at 100 degrees Celsius. Now we are dipping into an oil bath of 150 degrees Celsius. So the temperature measured by the thermometer will ultimately be 150 degrees Celsius, but it will follow transient behavior, and the transient behavior of this thermometer is captured by the first order system. So we will treat thermometer also as a first order system. So what will happen is the temperature recorded by the thermometer will keep on slowly increasing until it reach this final value of 150 degrees Celsius. So this we can call it as steady state value of 150 degrees Celsius, and at time t equal to 0, y of 0 was 100 degrees Celsius. And then we are given that if the recorded temperature is 130 degrees Celsius after 1 minute, that is after 1 minute, let's say at t equal to 1 minute, the temperature recorded by the thermometer is 130 degrees Celsius. So using this information, we have to find the time constant, that is tau of the thermometer. So we can say that the dynamics of the thermometer are captured by the first order system. The first order system, we write it as Kp upon tau s plus 1 is equal to ys upon xs, and since we are having the step input, we can write the response of this system as y bar of t is equal to akp 1 minus e raised to minus t upon tau. Now this akp we studied is the collective process gain, that is basically akp is y infinity minus y of 0. In our case, we studied that the y infinity or the steady state value is 150 degrees Celsius and the initial value was 100 degrees Celsius. That is, we can write this as 150 minus 100 is equal to 50 degrees Celsius. So this term is 50. And we have been asked to find this tau. So this y bar is the deviation variable, and at time t equal to 1 minute. We have been given that the temperature is 130 degrees Celsius. So y bar t, so this parameter is always the deviation variable, that is the initial value minus the value at time t. So this will become 130 minus 100 is equal to 30 is equal to 50. 1 minus of e raised to minus 1 upon t by tau, that is 3 by 5 is equal to 1 minus of e raised to t by tau. So time, the value of time is 1, that is we can get that 1 minus 3 by 5 will be 2 by 5 is equal to 0.4 is equal to e raised to minus of 1 upon tau. So you can take log and then solve and then ultimately find the time constant. So for this system, the time constant that you will be getting will be around, so it will be around time constant of 1.091. So you can take log of this equation and then take the inverse of that, is basically 1 upon ln of 0.4, so it will be giving you 1.091. So the time constant for this case will become 1.091. That is our final answer. Now let us discuss this question number 6. This deals, earlier we were having this step input, now this deals with the sinusoid input. So the question is, a liquid surge tank similar to the one described earlier in the class has the transfer function model of the form given by this equation. So we are having the first order transfer function model where h is the tank level. Basically this is the tank level, this is the input flow rate. The gain is 10 meter per meter cube second. The time constant is 50. Then the system is operating at a steady state of this flow rate and height of 4 meter when a sinusoidal perturbation of inlet flow rate begins with the amplitude of 0.1 meter cube per second and the cyclic frequency of 0.02 cycles per second. And then we have been asked 3 questions. So the first question is, what are the maximum and minimum values of the tank level after the flow disturbance has occurred for 6 minutes or more? What are the largest level perturbations expected as a result of sinusoidal variation in the flow rate? What is the effect of high frequency variation, say 0.2 cycles per second? So basically in this question, we are providing the input as a sine omega t. The input acts as a sine omega t, and we have been asked to find the output. So once we find the output, or else we don't need to find the output, but on the basis of this output, we have been asked to find the maximum and minimum values of the tank after 6 minutes, and also the maximum possible perturbation, that is the maximum possible level of the tank possible at any given instant, and also the effect if the frequency, that is 0.2 cycles per second, is very high, then what is the effect of that on the system. So that we have to discuss. So you can try solving this question. I will give you a couple of minutes. So right now it is 8:35. Let's say at 8:38 we can try solving this question. So over here, this 0.2 cycles per second, we are given frequency, that is f is equal to 0.2 cycles per second, and the omega is defined as 2 pi f. So this will be useful for you to solve the questions. We will discuss the solution once you are done with solving it. So let's try solving this question. So just to write whatever things we have been given in the question. So the first thing we have been given in the question is the gain. Kp is equal to 10. Then the time constant is 50 seconds. Then we have been given the steady state value of the flow rate and the height. And for the corresponding input, we have been given a sinusoidal perturbation, that is x of t is equal to a sine omega t, where a we have been given as 0.1 meter cube per second, and omega we have been given as 2 pi f, so it will become 6.28 into frequency is 0.002. This omega we have been given. Then we have been asked to find maximum and minimum values of the tank level after the flow disturbance has occurred for 6 minutes or more. So over here we can see that the time constant of the system is 50 seconds, that is tau is equal to 50 seconds, whereas we have been asked to find the response at time of 6 minutes. And we studied that at time of 5 tau the system will reach a steady state, that is in this case at 250 seconds the system will reach the steady state, whereas in the question we have been asked to find the response at 6 minutes. That means by this time the system has already reached the steady state. So in order to find the maximum and minimum values of the tank level at this steady state, we can straight away use the amplitude ratio formula that we studied, that is in this slide. For the response of the sinusoidal input, if this was the response, then the amplitude ratio can be written as the ratio of output upon the ratio of input amplitudes, that is given by amplitude ratio is equal to Kp upon under root of 1 plus omega square tau square. No, 1 plus AKP. Now in this given question, we can find the amplitude ratio, and then in order to find the maximum and minimum value, what we can do is we can just find the deviation corresponding to the steady state value in the steady state, that is the maximum and minimum value will be given by YSS plus or minus AR. Now in order to find the amplitude ratio, we can just replace all these values. So the A or the amplitude is given as 0.1 meter cube per second. Then Kp we have been given as 10. Then denominator omega we found out as 6.28 into 0.002, and tau is 50, this whole square. So ultimately you can calculate this and it will become 1 upon 1.18. That is, the amplitude ratio is 0.85. That is, in our case, since we are having A into Kp is equal to 1, we can simply write this equation, that is the maximum level at 6 minutes for omega is equal to 0.002 cycles per second will be 4 plus 0.85. So 4 was the steady state value of the height that was provided. So over here we have been provided the steady state operating height is 4 meter. So the maximum height will become 4.85 and the minimum height is 4 minus of 0.85 is equal to 3.15. So at 6 minutes the maximum possible height is 4.85 and the minimum possible height is 3.15. The second question we have been asked is, what are the largest level perturbation expected as a result of sinusoidal variation in the flow rate? That is, we haven't been given omega, but we have been asked to find y max and y minimum. So if you see, the amplitude ratio we found out as Kp upon under root of omega square tau square plus 1, and the maximum or minimum values are given as y plus or minus of AR. So ultimately, in order to find the maximum or minimum value, we need to maximize this value. In order to maximize this value, what we can do is we need to maximize this value, but since Kp is constant, we can, and tau is also constant, so these two are the parameters of the system that we can't manipulate. But this frequency of the input, that is A sine omega 2, this we can change. So if we observe that if omega is equal to 0, the denominator will become 0 and the amplitude ratio will become Kp, or let's call it as A times of Kp. So this will become our amplitude ratio, that is 1. That is, the maximum possible perturbation in the given system will be corresponding to omega equal to 0 and it will be 4 plus or minus of 1. That is, at omega equal to 0, we can say that we are having the maximum possible perturbations of plus or minus 1. So for this we found out that the maximum possible at 6 minutes, the maximum possible height was 4 plus 0.85, that was 4.85 to 3.15. And in order to find the largest level perturbation, we saw that omega tends to 0 will give us amplitude ratio of 1, and corresponding to that, the largest level perturbations will be 4 plus 1, that is 5, 4 minus 1, that is 3. And ultimately we have been asked, what is the effect of high frequency variations? Let's say 0.2 cycles per second. That is basically, if omega is very high, then what are the effect on the response? So again, in this equation of amplitude ratio, A Kp upon under root of omega square tau square plus 1, we can keep the value of omega as a very high value. So if this is very high, then the denominator will become more or less infinity. So 1 upon infinity will become no. So let's just put the value in this equation. So if omega is equal to 0.2, that is, frequency is equal to 0.2 cycles per second, then omega will become 6.28 into 0.2, then omega into tau will become 6.28 into 0.2 into 50, then this square will become a bigger value. So let's just find this value. .28 into 0.2 into 50, that is 62.8. Then the square of this will become around 3943. So we can put this value over here and get that amplitude ratio will become AKP upon under root of 3949. So this will become, okay, so it is 3943, so this will become 3944. Again, that will remain the same almost. Now we need to find the inverse. 1 divided by 62.4. So this will become 0.016 time of amplitude ratio. That is, if for high frequency, that is if omega tends to high, then amplitude ratio will keep on decreasing. That is, ultimately if omega tends to infinity, we can say that the amplitude ratio will become 0. That is what we can report. That is, for high frequency, the amplitude ratio will tends to 0. That we can say. So yes, this was the answer. The minimum of 3.15 to maximum of 4.85 at time t equal to 6 minutes for frequency of 0.002. Otherwise, the maximum possible perturbations are 3 meters and 5 meters. Or else, for high frequency variations, the output amplitude approaches 0. So I think this much is sufficient for today's class. In the next class, we will be studying few more complex problems in which we are having two different transfer functions for the same process. So basically corresponding to different input processes, we will be writing a combined transfer function and then we will study that. So I guess this much was sufficient for today's class. Meanwhile, I will just be here until 9 PM. So if you have any doubt related to the week 1, week 2 or week 3, you can ask me and I can try to solve that. You can write it in chat box or you can just unmute yourself and ask. So week 0 assignment was related to this Laplace transforms. Week 1 is mostly theoretical. And it deals with this process modeling and regulatory control, servo control, then empirical models, and then in week 2 we studied about this first order dynamical systems. So this was the assignment related to week 2, that is mostly theoretical. Then there are these few questions related to this thermometer. So this similar example I think we discussed in the class. Then these are corresponding to the final value problem, and again these are very similar to the questions that we discussed in the class. Now again in week 3 we are having the introduction to the second order dynamical systems. So we can discuss the second order dynamical systems and solve the questions related to that in the next class. So if you have any doubt related to any of these assignments, you can ask and we can solve, or else we can end today's call. Okay, so you can leave the class. I will be available till 9 PM if you by chance have any doubts. Okay, so I guess we can end today's class. Hope to see you in next class again. Thank you for joining.